continuity, which we talked about in the first unit, to derivatives, which we've been talking about for a while. So we're going to try to see if there's a connection between the two. So if you look at the name at the top, the relationship between continuity and differentiability. It's kind of a big word to say. So let's go ahead and just revisit. What does it mean to be continuous? Can we think about what the mathematical definition is, or kind of in your own words describe what it means for a graph to be continuous? What is continuity? Yeah?
No holes, jumps, or asymptotes.
No holes, no jumps, no asymptotes, graphically speaking. Okay? You can think about it as if you were drawing the graph without lifting up your pencil. Okay? What about the mathematical definition? The way you proved continuity in some of the examples we did at the beginning of the year? There were 3 things you had to check. Maybe that helps. In order for you to draw a graph without lifting up your pencil, these 3 things have to happen? Yeah? And they're the same. Good. The point exists, the limit exists, and they match up. So we'll say the point equals the limit. Good. Okay. Differentiability is a very similar idea. Okay? But instead of having the point and the limit matching, okay, if we're talking about differentiability, we're talking about derivatives, aka slopes. So in this case, I don't want to get too far ahead, but the slope from the left has to equal the slope from the right. It's a very similar idea to a limit. You know how to check the left and the right side to see if they match. For differentiability, we're going to check to see if the slope from the left is the same as the slope from the right. Okay, differentiability meaning derivative meaning slope. So we're going to try to check out what this connection is. Between continuity and differentiability, we're going to try to determine if a graph is continuous, does that mean the derivative also exists? Or maybe vice versa. If a derivative exists, does that mean the graph is continuous? Okay, can you draw without lifting up your pencil? No holes, no jumps, no asymptotes. So we're going to see which of those 2 statements is the true one, okay, is the correct one. And we're going to go through some graphical examples to try to make sense of that. So let's go ahead and consider this function first, specifically at the x value of 2. On the grid to the right, sketch a graph of f of x from your graphing calculator. So on your calculator, I want you to type in that function, use the window that the graph on your paper gives you, and I want you to just draw it, copy it down the best of your ability. Bless you. You know who that was? Yeah. Based off the sneeze? Yeah. That's impressive. Can we all get that graph? We can type it in our calculator. All right, so now that we have the picture of the graph, let's go ahead and answer some questions. Based on the graph of f of x, is it continuous at the x location of 2? Okay, so right there, you can think about no holes, no jumps, no asymptotes. Okay, because graphically speaking, we have the picture. Or you can think about, does the point and the limit match? Okay, in terms of those three rules. So, what do you guys want to classify? Are we continuous at 2? Yes or no, and then we'll talk about a reasoning. It's a little tricky because this is an endpoint. But we'll talk about that a little bit more. Let's see, at this spot, do you have a hole, do you have a jump, or do you have an asymptote? Graphically? No. Okay, so therefore you are continuous. Okay. Okay, yes, we are continuous. You could say because no hole, jump, or asymptote. Okay, but technically speaking, mathematically speaking, calculus speaking, we really shouldn't use that as our true definition. That's how you can think about it. Okay, but we really should use the point and the limit, like 3 criteria to help us out. So I'm going to put this in parentheses. That's how you can think about it, but that's not necessarily our justification. So if you were to look at this, okay, that spot of 2, does the point exist? Yes, we have a closed circle. Okay, so we'll say f of 2 exists. Now the tricky part is with the limit, because I know when we did continuity earlier, you had to check the limit from the left and the right to see it matched up. But since this is an endpoint, you really only have one side to check. So the limit as you approach 2 from the right, does that exist? Do you get an actual height out? Yes. So the limit as x approaches 2 from the right exists. Do the point and the limit match? Is the closed circle and the limit value the same? Yes. So we'll say f of 2 equals the limit as you approach 2 from the right. So a little bit of different continuity there because we're at an endpoint. You can only check one side, but the same criteria exists. You got to check the point, you got to check the limit, and you got to make sure that they're the same. So we are continuous. Okay. Then the next question is saying find the value of f prime of 2. Okay, the derivative at 2. So we could do this 2 different ways. We could try to tackle the derivative by hand. Okay. Or we talked about using the calculator, right, to figure out the derivative value. Maybe we'll do both, okay, just for practice sake. Let's do the by hand way first, and then we'll check to make sure it makes sense on the calculator. How do you want to approach the derivative of that function? Rewriting it might not be a bad idea, because it's a root. What shortcuts do you see? We got a chain, yep. Okay, so derivative of outside. Keep that inside layer. Once you take the derivative of the outside, you then have to move on to the derivative of the inside, which is 2x. Since we use the chain rule, okay, things are going to move to the bottom or the top of a fraction, depending if the power is negative or positive. Initially, maybe we can simplify. We have 1/2 times eventually a 2x. So the 1/2 and the 2 would cancel each other out, and we're just left with an x to the first, which would just be x. And then the x squared minus 4 all has a negative power to it, so that would move to the bottom. And you could change that 1/2 power back to a root if you wanted to. So there's our kind of cleaned up chain rule derivative. They want us to check the derivative or the slope at 2. So if you were to plug in 2 for the x's, we would get 2 over, yeah?
0.
Which is undefined. There we go. Okay, so by hand, we've determined that the derivative or the slope doesn't exist at that spot. let's go ahead and see if the calculator gives us the same value, or the same conclusion, I guess, because undefined isn't a value. So from last week, do we remember what buttons to press to figure out derivative on a calculator? Can someone refresh our memory? Yeah. Math, yep, option 8. We got to fill in some boxes. What goes in the first box? X. What goes in the second box? The equation you want to find the derivative of. Okay, so that would be like the original one at the top. X squared minus 4. You need an arrow over to move to the next box. What are we going to plug in for the last box? Thanks, Garrett. 2. Okay. And that derivative value is not real. Okay, doesn't exist. Undefined, whatever you want to say. So you get the same value either way. All right, so we can say then f of x is not differentiable. Good luck spelling that word or saying it. Okay, good luck. F of x is not differentiable, specifically at the x value of 2, because the derivative does not exist. So even though the graph is continuous, we determined that from the last question, the derivative or slope at that spot doesn't exist. Why do you think that is, based off the graph? Can we go back to the root definition of a derivative? When I say derivative, you think slope of tangent line. Okay, tangent line means touching a graph at one spot. So if you were to draw a tangent line at this point right there, what would the tangent line look like? Can you draw a line that just touches that spot? I could do that, right? Could I also do that? Could I also do that? Right? Do you see how there are multiple tangent lines? So how can you determine what the slope is when you have multiple lines? I could have a negative slope, I could have a positive slope, I could have a zero slope, all of that. So if derivative means slope of tangent, but you have multiple tangent lines to be drawn, there's no way you can figure out the slope, meaning there's no way to figure out the derivative, because you have multiple options. So that's why we're going to say here that f of x is not differentiable. Okay, the derivative doesn't exist. So in terms of something graphically to look at, if you are finding the derivative of an endpoint, the derivative doesn't exist. Okay, you have multiple tangent lines that can be drawn. Does that make sense? I hope. Okay, but notice how it was still continuous. That was interesting. It was still continuous at that spot, but the derivative didn't exist at that spot. So we're going to come back to that in a little bit. We're going to try to find a connection between continuity and differentiability. Okay, does the derivative or slope of a tangent line exist? Let's try the next one. Very similar setup, okay, just a different function to look at. So on your calculator again, I want you to graph that function. Bless you, bless you. All right, can we get that graph, that picture? All right, let's check out continuity first. So we're specifically looking at the x value of 0. Okay, that spot. Graphically, no holes, no jumps, no asymptotes, so we know it's continuous, but let's make sure we use the correct mathematical definition. Does the point exist? Does the limit exist? And do they match? I'd say so, right? The point is at 2, and if you approach from the left and the right, you would be getting closer to that height of 2. All right, so we're continuous. We can say f of 0 equals the limit as you approach 0 from the left and the right. So we're continuous at that spot. Let's see if the slope or derivative exists at that spot. So we're going to find the derivative. We'll practice it by hand. We'll check it on the calculator just to make sure. And then we'll go ahead and plug in 0. So looking at the original function, how might you want to find the derivative? Shortcut? Are we multiplying things together, dividing things together? Do we have an inside-outside? Do we have our power rule? Let's see, how do you want to find the derivative of x to the 1/3? We'll just work with that term first. Yeah? Power rule. We'll bring down the 1/3. Our new power is -2/3. Okay, so that's the derivative of the first term. We then have to add the derivative of 2, which is 0, so don't even bother with it. Okay, so if we clean this up, we have a negative power. We can move that to the bottom. And let's see, if we were to plug in 0 for x, what they want us to test, we'll have 1 over something. What is 0 to any power? It's 1. Oh, I'm sorry, it's 0. You're right. I'm sorry. That's 1 to any power I was thinking of. Sorry, guys. 1 to any power is 1. 0 to any power is 0. 0 times 3 would give us 0. Big whoopsie right there. Pregnancy brain to the max. 1 divided by 0? Undefined. Okay? So we can say f of x is not differentiable at x equals 0 because derivative does not exist. So let's talk about why this is in this case, because the spot we're checking in this one is not an endpoint. Okay, it's a little different than the last one we did. So if we're checking the x location of 0, we're looking at this point right here. Okay, if you were to draw a tangent line at that spot, what would it kind of look like? The drawing you drew, it might not be as exactly accurate as what's on your graph, okay, but if you really look at the graph to maybe figure that out, what would the tangent line look like? You see how it's like practically vertical at that spot? I know my hand drawing is a little off, okay, but if the tangent line is vertical, we know the slope of a vertical line is undefined, okay? So we can say, we'll label this as a vertical slope, aka vertical tangent. So it looks like, graphically speaking, if we have an endpoint that we're checking, the derivative doesn't exist there. If we have a vertical slope on a graph, the derivative doesn't exist there either. Even though it's continuous, okay, the slope might not exist, doesn't exist. All right, let's try another one. Consider this function, again at the x value of 0. Graph it. Is it continuous? Is it differentiable? We'll check those out. I kind of got ahead of myself. Did anyone do the last one on their calculator with the derivative? Did you check it?
Yes.
If you did, you should get undefined as well. Hopefully that works out. This graph always reminds me of when I was in elementary school and couldn't draw birds. That's how I would draw them, you know? Or you still draw birds like that? Yep. All right, so based off that graph, are we continuous at 0? Graphically, no hole, no jump, no asymptote, but if we were to actually use the true definition, does the point equal the limit? I'd say so. Yep. Yes, f of 0, bless you, equals the limit as you approach 0. So you have a closed dot there, and as you approach the left and the right, they're meeting up at that closed dot. Okay, so we have continuity. Perfect. Let's go ahead and tackle differentiability. Does the derivative exist at that spot? Bless you. Let's go ahead and find the derivative. So we'll have our power rule for the first term. Bring down the 2/3, subtract 1 from the power. Next we've got to add the derivative of 2, which is 0, so don't even bother. And then maybe we'll clean up the derivative because we have a negative power. If you were to plug in 0, we'd get 2 over 0, which is undefined again. Okay. You could check it on your calculator if you wanted to. Okay, you still should get something undefined, not real. So f of x is not differentiable at x equals 0 because the derivative does not exist. Okay, now something else is going on for this graph. The first one we had an endpoint. The second one we had a vertical slope. What do you guys want to classify this spot as? Yeah? A peak? Okay.
Something.
There's a lot of different things you could say. Peak? Is that how you spell peak?
Yes.
Yeah. P-E-E-K, is that the peak with your eyes? I'm not an English person. Sharp point. You might see the word cusp, actually. Sometimes in problems or word problems, it'll come up as cusp. So some type of peak, sharp point, cusp, anything like it that's a drastic change like that, okay, we'll classify as a point that is not differentiable. Okay, and again, if you think about the definition of a derivative, the slope of a tangent line, how many tangent lines could you actually draw at that spot? You'd have a lot at that sharp point. So there's no way you can actually determine what the slope is if you have multiple possibilities. So we have three different things that we got to look for in terms of not having a derivative. Graphically speaking, you could have an endpoint, you could have a vertical slope, you could have a peak, a sharp point, a cusp, any of those. Okay, but there are some other ones because we're going to finally talk about this connection between continuity and differentiability. So based on those three examples, what do you think the connection is? Does continuity imply differentiability, or is it vice versa? If a graph is continuous, does the derivative exist everywhere? No. What about vice versa? If the derivative exists, is it continuous?
No.
Well, we didn't really investigate the reverse statement, okay? But let's say, for instance, this vertical slope one. If you were to pick a spot anywhere on here, and you were able to draw one tangent line, are you going to be continuous at that spot?
Yes.
Yes, because in order for you to have a spot to draw a tangent line on, doesn't mean the point has to exist. And if you are able to draw a tangent line, you have to have some type of left and right side connecting so you can figure out how to draw the tangent line, the path of it, right? So if you thought about the reverse statement, that one's actually true. Okay, so we're going to say differentiability, the fact that the derivative exists, differentiability implies continuity. Okay, so if you know a derivative exists, you also know it's continuous. No holes, no jumps, no asymptotes, the point and the limit match. Okay, so basically this is saying if the slope exists at a point, then the point equals the limit. If you're able to draw a tangent line at one spot, you know that the point exists at that spot and the limit exists. Okay, you're continuous. So in order for a function to be differentiable, we're going to have to check two things. Okay, one of them is continuity. So in order for the derivative to exist, you must be continuous. But then we also have to check out that slope idea that I kind of mentioned at the beginning, where you have to check the slope from the left and the slope from the right. So we're going to jot those two things down here. So f of x must be continuous. No holes, no jumps, no asymptotes. The point equals the limit. Okay, so you're going to check continuity at a specific spot. But in order for you to be differentiable, okay, we're going to have to check the slope from the left and the slope from the right. Make sure that the slope values match as well. So in terms of limits, we're going to check the slope, meaning derivative, from the left of some x location, and make sure that's the same as the slope, aka derivative, from the right-hand side of an x location. Notice how I'm using f prime instead of f. We got to check the slopes. Okay, so in order for the derivative to exist, you have to be continuous, but you also have to make sure the slopes match up. The slope from the left is the same as the slope from the right. So we're going to check out those two ideas in this, the next question here. So we have this function, piecewise function. Is g of x continuous at 3? So this is a throwback to kind of the first unit that we did with continuity. We got to check those three things. Does the point exist? Does the limit exist? And do they match up? So let's check out the point first. If you were to plug in 3 to check the point, which piece of that piecewise function would you use? The first one, good. So if we plug in 3, square root of 4, which is 2. All right, so we know the point exists. Let's go ahead and check out the limit. So we have to check the left of 3 and the right of 3. Which equation should we check to resemble, or not resemble, to represent the left-hand side of 3? The first one again. So if you were to plug in 3 into that first one, we already know we should get 2. If we plug in 3 for the right-hand side equation, which would be the x, or 5 minus x, looks like we also get 2. Do the point and the limit match? Yes, so we can say g of 3 equals the limit as we approach 3. So g of x is continuous at x equals 3. But remember, just because it's continuous doesn't mean that the derivative exists at 3, because those last 3 examples we did were all continuous, but the derivative didn't exist in any of them at a specific spot. Okay, so continuity does not imply differentiability. There's the second thing or second step you have to check. Okay, do the slopes actually match up? Is there only one tangent line from the left and only one tangent line from the right that would match up to give you only one tangent line at that spot? So it's going to look very similar to this, but we're just going to be checking the derivative this time. Okay, so let's go ahead and check out the left-hand side. The limit as we approach 3 from the left. Now before, we said that the left-hand side was representative of the square root equation. We have to analyze the derivative of that square root equation, the slope from the left. So if you were to rewrite this, how might you want to find the derivative? We have x plus 1 to the 1/2. What shortcut do you want to use? Chain. Alright, so bring down the 1/2, keep the inner layer, new power, times derivative of inner layer is 1, so don't even worry about it. We can maybe bring the quantity to the denominator because it has a negative power. Alright, so if we were to check the slope, aka derivative from the left, we'll plug in 3. Four to the 1/2 power. So same as the square root of 4. So that'd be 2, and then times the other 2 that's out front. Looks like the slope from the left is 1/4. Alright, slope from left. Let's check to make sure that that's the same as the slope from the right. Alright, so the right-handed side of 3, we had 5 minus x. Oops, sorry. We're not going to write that down. We need the derivative of that equation, which would just be we think a -1. If you tried to plug in 3, you would get -1, right? Slope from right. So what do you think? Are we differentiable at 3? Does the derivative exist? Does the tangent line from the left match the tangent line from the right? Unfortunately not. Okay, so even though this function was continuous, the derivative doesn't exist. You have different tangent lines approaching at the same spot. Okay, think about it. If that's happening, you're creating some type of sharp point, perhaps, because this slope is drastically different from this one. All right, and if they're drastically different, that's going to cause some type of cusp or sharp point, graphically speaking, which means the derivative doesn't exist. So we'll say, since the left and right slopes do not equal, you can say g of x is not differentiable at 3. You could say g prime of 3. Okay, the derivative at 3 does not exist, something like that. So even though it's continuous, the points there and the limits there, the slopes are not matching up. We did all of that without a graph. Okay, so we're going to use some calculus to help us identify those characteristics. We'll stop there for today. We're going to have 2 more examples kind of similar to that, okay, tomorrow to check out in terms of continuity and differentiability. But this is a big idea, guys, okay? Whenever you see the word differentiable, that means the derivative exists, but it's also implying that you are continuous. No holes, no jumps, no asymptotes. So the moment you see differentiable, you can also assume continuity. they imply, or it implies the other. Okay? In terms of your homework, I think we'll be okay. Let's see, can we do number 1 real quick, just so I can make sure we understand kind of what's going on here? Or that you understand what's going on here? If you take a look at that graph, can you identify some values for x for which the graph is continuous but not differentiable? Where you can draw it without lifting up your pencil, where there's no hold, no jump, no asymptote, but the derivative doesn't exist? Yeah.
X equals 2.
X equals 2, why?
Because it's continuous, but slopes on each side of it.
The slopes on each side are different. Notice how this slope is kind of shallow, where this one's steeper, this one's negative, this one's positive, right? You could say that. You could say graphically there's a sharp point. Didn't we say that was one of the graphical characteristics? All right, so x equals 2 because sharp point. Or slope from left doesn't match slope from right. That's fine. Is there another one? Yeah. Is an endpoint. Is there another one? Good, Vinny?
6 is an endpoint.
There we go. Good job. All right, I think you guys are good.